All right. Hi Abhay, hi Midli, hi Prezi. Hello Yashwant. So are you able to hear me clearly? Should we start now? All right. All right. Great. Only Abhay, Midli and Prezi is not able to hear. All right. Great. All right. So this batch seems to be doing great work. And looking at your assignment of Pig and Hive, I'm impressed. All right. And yeah. All right. So we discussed about, did we discuss about this story last time? All right. Let's just go over the story again because I think I finished this story. All right. So this story is quite a real story, and it used to be quite common in earlier days when we did not have a public solution for handling such amount of load. So on initial public launch, a startup would just move their product from local workstation to a shared and to a shared remotely hosted MySQL instance with perfectly defined schema. And now, as the service become popular, there'll be too many reads hitting the database. Okay, so the quick solution to such kind of situation was we add the memcache to to our architecture, and everything starts becoming smooth. Okay, and what does memcache do? Memcache basically caches common queries. What does it mean by caching? If there is a query which is coming again, it will create, it will save the results in the in readily available so that it just look up the query in the table and then give out the result instantaneously without consulting the DB or the app. So memcache is quite powerful and quite well known in the industry. And as a matter of fact, probably if somebody asked me what was the people's favorite NoSQL data store, it would be Memcache. Okay. Now, all right. So reads are no longer strictly ACID. The important thing which we all should understand that whenever we are caching the data, it generally means that there are two copies of data, one with the cache, one in the DB. Now the copy in the cache is something which keeps on getting served without consulting the DB, right? And whenever there is a change in DB, the change is propagated to the cache. Now, here is the problem. So if there is a change in a DB, it will take some time to reach to cache, and there might be a difference of 1 second or 2 seconds, which means for 1 or 2 seconds during the time where cache was getting updated, the data served to the users is inconsistent, right? Data served to the users is inconsistent. So you can see that now reads are not strictly acid, as in it does not have all the properties of acid. And what does it mean by acid? Atomicity, consistency, isolation, and durability. These are the four characteristics of any data transaction, of any database. So these four characteristics are something which everybody likes to stick to in relational world. So, and anywhere these four, either of the four characteristics is violated, it's very alarming to the DBA. All right. Now, as the service grows to continue, too many writes would be hitting the database. This is the problem which you would face. And in this scenario, what we used to do was scale MySQL vertically by buying better hardware, such as 16 cores and 120 GB RAM and banks of 15,000 RPM hard drives. Now, this solution is costly, okay, but that's okay because our product is getting popular. That means money is not an issue for us. Now, as the service grows in popularity, we just bought this hardware. Now, theoretically, this would be the e- end of the problem. We'll be no longer facing any kind of these problems. But no, no matter what hardware you buy, you would end up with a lot of you may not be able to cater to the users. Okay, so so this thing works for a couple of months, maybe a month or so, but uh, and in the meantime you raise some fund and you have new features which have increased query complexity. Okay, so for example, what does it mean? Let me explain. Let's say you're working on a simple e-commerce platform. Now you realize that you have got enough popularity. Now you start doing all kinds of feature development. You have now 10, 15 product managers, and every product manager is trying to add some more feature. Such as one is coming up with the idea where people can write the reviews, other have come up with the idea where people can suggest attributes. Somebody has come up with the idea of say having different price, combining prices with others, and so on. So there are hundreds of ideas uh, which people will start working on. And interesting thing about all of these ideas is they change the product definition. Most of these things create more database tables. And while we serve the page, we might have to consult all the tables or join all the tables and then give the product detail page. Now, now this is just one example in case of e-commerce. So if you see, if you go to Amazon and click on any of the products, and you will see lot of details, right? There is a product image, there is a product title, there is a product author, then there is what do you call variations, then there are details, then we call them detail bullets, then the features, then the big text under which is described, then there are reviews, then there are so many features, and those are the things I'm talking about here. So as the new features are added, the complexity of query will keep on increasing. Now there'll be too many joins. So one solution to such kind of scenario is that instead of joining every time the user comes in, first attempt was that let's just cache the whole product. Okay. Second, this attempt currently which we are talking about is the we denormalize, meaning we keep a big sparse table in which we put all the tables in once. Okay, we'll talk about it as we go forward. How do you denormalize things? Okay, instead of having, let's say, two tables, one for students and other for courses, you merge both of them together. Okay, now this way you will be saved from joins. Okay, you'll be saved from joins, but this totally will annoy the DBA. And there's a reason for it, because as part of our usual DBA knowledge, we are supposed to normalize, not denormalize. Denormalization is a rare situation. Denormalization is the rare situation which none of the DBA is taught in this in the school. Okay, so for example, the first denormalization I encountered was early in the career when I, for working for DE Shaw, where we were working on, say, a reconciler. When we had reconciler and I was supposed to join around 40 tables. Okay, so it was very time consuming. For lot of work, it was taking above 5 minutes. Okay, A- after I had all kinds of you know, after I had all kinds of indexes in place. So there was no scan happening, and still the whole query was going beyond 3 to 4 minutes. Now, to avoid that situation, what we had to do was we had to denormalize so that we can avoid joining tables. And that helped a lot. That helped a lot. Specifically, when your data is really big, that you can't even you no matter what you end up scanning through a huge amount of data, even when so when the data grows to such a big size that even the indexes become slow. In those circumstances, you the whole theory of DBA is actually when the index size when you try to query a table and you realize that even after creating indexes on the table is taking so much time, then you have to reevaluate your approaches. And that's the end of the at that point of time when indexes are slow, that point of time most of your DBA knowledge goes for a toss. Okay, when I'm talking about indexes being slow is generally a situation when index can't fit into the memory, and that can occur when you have really huge DB. Okay, imagine that you have around 50 terabyte of data, or maybe say even with 1 terabyte of data, and each column might be something, and the total index size might be something like 10 GB. And when you have 10 GB index size that cannot fit into the memory, so the searching over the indexing also goes to the disk every time. So in all these scenarios, when joining becomes complex and joining takes a lot of time, you try to denormalize so that you don't join. Instead you just read the whole row and represent it to the user, and that improves a lot of things. Now next thing is, once you did this step, next thing would happen is that you are still becoming more popular. Your service is really popular, and though it's a nice thing to have, it's a happy thing to have that people are using your service, but things are going to be slow. You need to handle that. And so what you start doing is all the logic that you are running on the server side, such as you are having stored procedures, you are doing, say, currency conversions, all of that. You stop doing that on server side. Instead, delegate it to the client. Okay. Say, for example, you're doing time conversion, currency conversion, and you are also trying to do kind of backend processings like for example various kinds of things that you could delegate to the client itself. Okay, so in all those kind of scenarios, You stop doing server-side computation and you delegate it to client. Now, these small steps would save you from a lot of headache. All right. Next, you do is that you realize that some queries are still too slow, so you periodically pre-materialize them. What does it mean? Let's say, let's take a case of Amazon. Okay, there are some products, say top 200 products. We know that these top 200 products will be people will be seeing them again and again and very frequently. So what we do is we prepare their the whole product instead of joining and reevaluating this that. Instead of that, we prepare the whole HTML and keep it with us i- upfront. We know that these 100 pages are very popular, or these 500 pages are very popular, and so we keep on pre-materializing most of the complex queries. Okay, so complex query, if we encounter it, we just serve from pre-materialized data. Okay, and try to stop joining in most cases. At this point of time, reads might be okay, but writes would get slower and slower. At this point of time, you will drop all the secondary indexes and triggers. Okay, all right, all right. So, what did we learn here? What did we learn here in this the case study which we went through? We After all of these optimizations, in order to cater to the load, we did a lot of things. And what were those things? We no longer have ACID properties of database. We no longer do any server-side work such as stored procedures, okay, triggers, stored procedures. We no longer have secondary indexes. We only have primary indexes. And we basically no longer have any of the stored procedures or what do you say? So we have no ACID properties, no server-side things, and no secondary indexes. Now, if you look at it, that's what is a NoSQL. So, in essence, we tried our best. The only thing we did not do in case of RDMMS. So, even after these 7 steps, there'll be if the service still grows in popularity and we can't handle it, there'll be next step called sharding. We install multiple MySQL servers or multiple Postgres servers, and we divide the load amongst them by using some kind of a program by programmatically switching between the various databases. And if you notice, it's a natural progression. The NoSQL is a natural progression in order to cater to this kind of scenario. In order to cater to this kind of scenario. All right. So, so this case study says that there are so many features of MySQL or any database, a relational database, that you don't require or you will have to do away with them when you go into the crisis where there's a lot of load to be handled. All right. So that's where the NoSQL comes into play. Okay, that's where most of these headaches are already taken care by most of these NoSQLs. The one thing after this step, after this step, if they could not shard their database, shard means dividing a database into multiple databases, dividing a table into multiple tables, one for say users whose name starts with A, second for those users whose names start with B, and third for the users whose names start with C. Okay, so this way, if we divide the DB into these sections, okay, this kind of multiple sections, and have these, sorry, we split the table into say 10 sections, and those 10 sections are being handled by 10 different database installations on 10 different machines. And that kind of attempt, all those people in 2004 2005, all those people who could shard and scale, they survived. Rest of the companies actually vanished because those people could not handle the load. Because after this step number 7, up to step number 7, everybody did, but after step number 7, not many could do. And that's where that's where that's where Amazon kind of companies came into play, and and published the paper like on NoSQL, and that became the next generation of databases. Yes. All right. Okay. So so the previous example would have given you a lot of ideas. Okay. So why do we need NoSQL? One, big data. To handle big data, it's as simple as that. When you have to store humongous data, process humongous data, your usual databases cannot handle it so easily. And that's where we need a NoSQL. Second, for high availability, to cater to the high availability, to cater to many concurrent users. Third, for scale out architecture. Okay, for scale out architecture in the sense that today you have few users, so few machines are good. Tomorrow, if you have many users and you need more machines to cater to, you should be able to add more machines easily without having to worry about. So while on one hand we are talking about high availability, it should be able to cater to many users, meaning in case one machine goes down, some other machine can take care of it. Third is Third is scale out architecture. And when we say scale out architecture, if if for scaling out you use really high end hard architecture, it does not make sense. So generally, whenever any software says that, hey, I have an scale out architecture, it generally means that commodity hardware is welcome. Commodity hardware, as in what does it mean by commodity hardware? Commodity hardware means a hardware not very high end, but it does not mean the hardware which is faulty, old, or low end. No, it means a decent hardware and okayish price, but not too high price as blade servers. Okay, so instead of having monolithic architecture and expensive, your software, this NoSQLs generally scale out. Okay, scale out, or what do you say, there was another term which we were using, horizontal scaling. Okay, so what exactly is NoSQL we are talking about? NoSQLs are designed for distributed, and they are generally not having schema. The primary key, foreign key, the rigid table structures, none of these NoSQLs are able to provide it. Okay, so the most important aspect of any NoSQL is distributed. If somebody comes and says, I have got a great database which is NoSQL, just because I'm not able to provide SQL, my first next question would be that on how many machines can it scale to? Okay, so that's distributed architecture. That's the most important criteria of NoSQL. Now, rest of it is a side effect of being distributed. Let me explain how. So when we say something is distributed, it's going to distribute data, right? And in case of database, it is ideally supposed to distribute a table because table grows row by row. Now, if it can't grow, it can't distribute the table, then it won't be able to handle huge data. And if it's able to handle table in a distributed manner, meaning it's dividing the table into parts and putting those parts on multiple machines. Okay, if you are putting the parts on multiple machine, you need to be able to identify every row with a handle, and that handle is an identifier. Okay, so every NoSQL servers, because they are distributed, or you can say that every distributed server where table is divided and sliced and put it onto multiple machines, every record has to be every record has to be identifiable. Otherwise, it won't be possible to figure out where is what. Okay. Next is the NoSQL. It was basically a Twitter handle. There are many reasons. I mean, they just kept it Twitter handle. Now people are making finding out the full form of it. Some are calling it not only SQL. Some are calling it new SQL. Some are calling it non-relational, and so on. But most important thing is to understand the other qualities like distributed architecture. Next is horizontal scalable. So the two properties, one distributed architecture. When we say distributed, generally this horizontal scalability is something that comes along. Okay, so and whenever you are launching a new database, you cannot reach to the public so easily, right? Because it's very difficult to convince people to your database to put their data into your database. Why? Because in case your company shuts down, I had a tough time selling my product called T-Bits because it was kind of a document management system and their data used to go into T-Bits. Okay, I had a tough time because because people were really worried. What if this guy or what if this small startup shuts down? What happens to my data? Okay, the only way I could make my sales were by sharing with them my source code. Okay, so we signed the agreement with all our customers and said, in case we shut down, here you will get the copy of the source code. Okay, so that was kind of agreement we had to do, and that's very important because every company, when the most important thing they do is their data, right? In case they are not able to access their data even for 1 minute, there are high chances of dispute. So the idea which I'm trying to drive to is, when you are building any data intensive product, the acceptance would be very low. To counter that acceptance, you will have to, the most easiest way is to make your software open source. Okay, and open source does not mean that you do not charge for it. Okay, the commercialization is another aspect. So like for example, all Hadoop tools are free, but for support, Hortonworks, Cloudera, Mapr, Qbol are charging quite a much. Okay. All right. So it's open source, and it so every NoSQL has to be open source. Otherwise, nobody will buy them. Nobody will use the software unless it's Oracle or SAP or somebody else. Next is it's horizontally scalable. Okay. So this we have already touched upon. Next point is schema free. All right. Schema free. So when you're dealing with NoSQLs or when you're dealing with humongous data, if you have restrictions of schemas, you won't be able to survive. You because survive the load. The way in the case study we saw. Next is the easy replication. What does it mean by replication? It, there must be. It should be quickly. It should be very quick to establish another machine and replicate the data. Okay, so that's kind of a secondary attribute, although because it's a part of distributed architecture. And simple API. This is an excuse. Honestly, I'll tell you. So when you hear this simple API, it's an excuse saying, "Hey, we could not write a tool which could give you single SQL query. Therefore, we are giving you a simple API." Simple API as in kind of a get and put. Okay, kind of get and put. Next is manage use data and commodity hardware, and there are more than 150 types of NoSQLs. All right. So before moving forward, let's understand what are the different kind of NoSQL databases. This categorization would keep getting updated from time to time. This categorization is not something written on a stone, but it's important to understand the general categorization. First one is column oriented or white column. Okay, Accumulo, Cassandra, HBase. Those are the kind of databases. We'll go into the column orientedness in detail. We'll take an example and then we'll go into it. So column oriented are very similar to our normal database tables. Okay. The only difference is in the way the data gets stored in files. We will talk about it as we go forward. All right. Next is document-oriented NoSQLs. What does it mean by a document? A document you can think of is a big object. So, so you can say that a document is a big object. All right. What does it mean by an object? The way you must have read in C you have structures, in C++ you have class, in Java you have class, and JavaScript you have class. So everywhere you create an object out of those classes, and the object has many properties. And those properties are, you can always think of them as name and value. Okay, the name are generally hard coded as part of the definition of a class, right? If you think about an object, it's nothing but a collection of name and value, where name is a string, okay, and the value is a big object, or value could be a primitive object, or value could be an object of the same class. Okay, in the exact same fashion, in exact same fashion we have document, and document oriented database exactly do that, as in they are big object stores. For example, in case of MongoDB, the document means a big JSON object. Okay, and JSON is exactly what I just explained. It has key and value. Value could be an array, value could be another object, value could be a primitive type such as string, number, or something else. Okay, so for so a document oriented database is something which can help you store the whole document. Now you can query various documents based on their properties of the documents. Okay, the way you have indexes, similarly you can query based on the documents. Okay, that's a document oriented database. The most popular one in the market are MongoDB and CouchDB. Okay, for the document oriented database. Third one is key value pairs, key value kind of database. These are the most primitive and the initial kind of database. These are something which started the whole war of NoSQLs. So the first one amongst all of these were Dynamo from Amazon. So Dynamo was the first inspiration for most of the NoSQLs, because at one fine day, Amazon realized that they could, sorry, on the, I think on 2003 or 2002, uh, when Amazon was badly shut down on Black Friday as well as on Christmas. They realized that they can't live with it. So one of the engineers said that we are not going to use database for these things. So let's just build a simple kind of a hash table, kind of a key value properties, which is distributed, which is kept on multiple machines, and let multiple machines cater to it. So the architecture of Dynamo was extremely simple in the beginning. It was basically a distributed hash table. Hash table is like key value pair, collection of key value pair. The only quality of this hash table was some of the keys are in one table, some of the keys are in another table, and so on. And then came Memcached. Memcached is something everybody uses, even if they don't know anything about NoSQL or anything. You talk to any web programmer launching their PHP, they would know about Memcached. Okay, because that's what they do when the server gets a lot of load. Next is the project Voldemort and Redis and Reich. Okay, we'll get into a little bit more details about Redis later on. Okay, now there's a graph databases. Those graph databases are also quite useful these days. Okay, so say Giraffe and Neo4j are two which are being used by many people. So when you have to store complex graph objects, as well as you have to query on graph, there are many algorithms you could run on graph, such as finding page ranks, such as finding common friends, and so on. So for those kind of circumstances, for those kind of problems, you would use a graph DB, or finding how A is connected to B or how A is connected to Z. So those kind of situations, those kind of graphs, okay, those kind of graphs basically need to be stored and queried, and those algorithms need to be applied. In those circumstances, you might use graph. Okay, so you might be wondering that what if I have a need for relational, I need a key value store and a graph. Okay, what if I have all three kinds of need? Do I need, should I use three databases? Yes. If your data is sizable on all three aspects, then you go for three databases. If your if your data is only the one which is big, if let's say you have five tables, out of it there is only one table, the one that is representing graph is really huge and you cannot afford to be slow on querying the graph. In those cases you go with only the graph database, and you can emulate the smaller table as well on those databases. Okay, now this is a kind of a traditional summary between comparison between NoSQL and the SQL. So while one was while most of the SQL database follow the CORD principles, follow the same standard relational theory, there are only minor differences. And in NoSQL, There are many major differences. Okay, so one started in 1970s, other started in 2000s. Okay, age difference of 30 years. And the examples where we have MySQL, Postgres, Oracle. On the other hand, we have MongoDB, Cassandra, and HBase. While one is of strictly relational and other varies on data types. Here you have structure and data types are fixed in advance. So when you create a table, you upfront define everything, right? But in case of NoSQL, you don't. Okay, for scaling vertically, so this database could scale vertically, while NoSQL could scale only could scale very well horizontally. Okay, what does it mean? In SQL database, when you are in crisis, you generally end up buying a lot of hardware. While in NoSQL, you can simply increase more number of machines and be happy. At one end, you have the development model as mixed, while in case of NoSQL, almost all new generation databases are open source. Okay, the transaction support is there in SQL databases, strictly transactional, as in they have all four properties of transaction A, C, and I and D. Okay. In case of NoSQL, in case of NoSQL, okay, the the generally the transaction is supported on each record label, that you can modify the record in a single transaction so that others won't see your changes and others won't see your changes in trim changes, and others won't modify half of it and you will modify half of it. That won't happen. So on record label, it provides the transactions. Most of these NoSQLs, they do not, none of them seem to provide the table label transactions. Reason being, the table gets divided on multiple machines, and effectively you won't be able to store things in table. So if you have kind of a lock that nobody should be allowed to store into table while I'm storing something, that's not possible. Okay, if we try to do that, the whole database becomes extremely slow. Okay, so in case of SQL database, we use SQL. In other case, there are APIs, and consistency is configured for strong consistency by default. The SQL databases, while in case of NoSQL, it depends on the products. All right, now this is something very interesting I would like to discuss. Okay, I'd like to discuss this part. All right. All right, let me just. All right. How do you gently? Okay, never mind. So okay. So far I have tried to establish the importance of a NoSQL. I tried to put down the case study on the usual case study and a little bit of history and categorization of NoSQLs. All right. Now let's talk about the something which is very important. As I told you that NoSQLs do not provide that kind of strong consistency. And I tried to give you a little hint why they could not provide table level transaction and so on. Okay. So there is something very interesting aspect. So this guy, the scientist called Eric Brevister, he came up with a big excuse. Okay, so so whenever he said that it's not possible to provide consistency in NoSQLs, people did not like it. Nobody believed it. So then he had to put down it like a theorem. Okay, so he observed that there is a reason why NoSQLs can't provide you the amount of consistency which relational database can. Okay, what does it mean by consistency? Consistency means that all the nodes in, so if there are many users accessing your database from many different places, all those users who are accessing your data, they should see the same data at the same time. Okay, sounds easy. If you're coming from relational background, you'll feel that it's quite obvious that all the users should see the same data at the same time. Correct? But okay, so we will talk about why it's not possible. But let me just define few more things. Okay, so CAP theorem says that you cannot have all the three things: consistency, availability, and partition tolerance. Okay, so Brewster, or it's also called Brewster theorem, he said that you cannot get all the three things. You can get at most two of them. Okay, you can get consistency and availability. You can get availability and partition tolerance, but you cannot get all the three things. So, okay, availability means a guarantee that every request receives a response about whether it was successful or failed. Availability means that requests get scattered, whether there is an error or not, the customer gets informed. It should not get into something kind, never got responded, the user kept on waiting, and so on. Okay, the request should be addressed. That is availability. The more number of requests you are able to respond to, the more available you are. Okay, if you are able to request 100% request, you are 100% available. Okay, next is the partition tolerance. What does it mean by partition tolerance? It means that how many machines can you shut down in order to cater to the end user. Sorry, how many machines can you shut down and still cater to the user? So the system should continues to operate despite arbitrary message loss or failure or part of the system. Okay, so you have this 10 databases running continuously. Even if one of them shut down, still the user should not be impacted. Or two of them shut down, still users should not be impacted. So the thing is, so more number of loss you can tolerate, the more partition tolerant you are. Okay, so these are the three things. This is the definition. So CAP theorem says out of these three things, you can at most have two. You cannot have consistency, availability, and partition tolerance at the same time. Can anybody help me understand why? All right, let me explain. It's so it took me a little bit time to represent it graphically. Okay, so the representation which you see next may not be like 100% perfect, but it will give you a great idea why it's not possible to give CAP. All right, let's have a look. Let's have a look at the first. So these are the three kinds of systems I could come up with. If you have more ideas, like you think that there could be one more architecture, then I would like to discuss it. Okay, so CAP theorem says that the out of CAP only three are available, and this diagram shows you three kind of architectures. First one is your typical RDBMS. Your typical RDBMS where what's happening is there is a single machine. Single machine, all the users are reading, writing from the same machine, right? All the users are talking to the same server, writing and reading from the same server. Okay, so what does it mean is the 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 if one user is reading or writing, it might be blocking the other reader writer, right? Also, in case this machine goes down, then the, all other users won't be able to access the data. The data is gone. Therefore, this scenario is consistent but not available, meaning if one user is accessing a particular row, the other users will have to wait. Or if there are limitations on the server part, that only these many people can actually access it, and if there are many users, they'll have to wait in the queue. The queue will be longer in this case, therefore it is less available. So if the queue is smaller, then your database is more available. If the queue is bigger, if the queue of people waiting for some service is bigger, that means the service is not greatly available. Next is the partition tolerance. If this machine goes down, the data is gone, there's nothing left, right? So users won't be able to access the data if this machine gets shut down or something happens or network problems occur. Therefore, a typical RDBMS is not available, not greatly available, and not partition tolerant, but it is consistent. All the users will see the same data at the same time. It won't happen that one user is seeing some one data and other users are seeing some other data. You ran the select query, you got different data set, and I run the select query, I got a different data set. That is inconsistent. Okay. Okay, so we have all right. So we have Yashwant's question. Let me save it. All right. Today is what date? Today is 30th. All right, we'll talk about it. Just give me a minute. All right. In case you have the point I'm trying to drive here is in case you have set up a single machine, which is that then you want to have consistency and availability. Okay. Now in the second diagram, so you can see Yashwant, the last one, the third one, it generally are you talking about RDBMS with backup. Okay. So now I will also talk about the other scenarios. Now second diagram is quite interesting. This is the typical architecture of most of the NoSQLs. So what people did, let's say the people like MongoDB and others, what they did was they created multiple servers, say A and B. All the users will write to A and the data from A flows to B and all the users can also read from B. Okay, let me go again. So the users can read from both A and B while they can only write to A. All right, so only in case of writing A is a bottleneck, while for reading you have many servers. Okay, the data from A gets copied to B, and now you can obviously see that during the time the data is in transit, the data is traveling from A to B, during that period, people will be seeing the stale data. While A has said that, hey, I've written my data and I've done my job, while B is still seeing the older version of data because the data is taking time to reach from A to B. All right. So this is something that makes a NoSQL or a databases like MongoDB inconsistent, although it's heavily available and is partition tolerant. In case, let's say A goes down, all the users can shift to B and start writing to B. Therefore, it's fairly partition tolerant. Similarly, in case of MongoDB and Zookeepers, there is an automatic election where A gets elected by itself. Nobody nobody configures A to be the master or A to be somebody who accepts rights. Okay, so you can see that this kind of scenario is generally called eventual consistent. Okay, the in long run everything is going to be all right. Okay, so the word consistent scares people. The word inconsistent scares people, and therefore there's a the word which we use here is that our system is eventually consistent. We are not inconsistent. We are eventually consistent because after some time the data from A is going to be synchronized with B. So the B is going to be having the same data. We are not losing or corrupting any data. It's not on inconsistent. It is eventually consistent. Okay, so that's a kind of diagram. There's a kind of architecture. We will see the elections during the discussion of Zookeeper. Okay, and third one is RDBMS with backup. Okay, RDBMS with backup as in you have one machine A, all the users are writing to A, and the data is getting replicated to B. Okay, all the users are reading writing from A, while a copy is kept in the background. So every time we make any change at A, the data get pushed to B. Okay, in case we lose A, we can bring B back. Now, can anybody recollect which architecture is this in Hadoop ecosystem? Anyone? Correct, Yashwant. Correct. Anyone else? Yes. So my question is this third diagram. Did you see some architecture which corresponds to it, where all the users are reading writing to something and the data is getting replicated somewhere? So did you notice this? Do you think? Let me see if somebody is coming with it. Okay. So do you think A is name node and B is a secondary name node? Yeah. Correct. Correct. Good. So A is kind of a name node and B is a secondary name node. Now, good part about this, the difference between second diagram and third diagram is while second diagram is little inconsistent, while third diagram is totally consistent because whatever is being written to A, there's the same thing being read by other people. Therefore, A this in third diagram, the A is strongly consistent but is not available because all the load is coming to A, so the queue is going to be bigger here. All right, all right. So does that answer your question, Yashwant? So what he's saying is that in a typical installation of Oracle, will have multiple servers based on the size of data. So generally, are you generally splitting the data on multiple Oracle servers? Okay. Okay. So what they're trying to do is they are trying to do manual sharding. Okay. That is something you will notice that happens in NoSQLs manually, automatically. You do not have to basically even think about having multiple servers. All right. All right. So in most of the world, when we were dividing the data, we were dividing the data by ourselves. Okay. We were all the time busy in managing the data, moving the data, and kind of involved all the time in all the data operation. While that work is something absorbed by NoSQLs. All right. Now, we talked about column-oriented database. I would like to take a little digression and would like to explain what does it mean by column-oriented database. Okay? Okay. Vishwa's question is, availability corresponds to no response from server, but in example, it is evident that the request will be delayed due to longer queue to be served. Yes. So what happens is that I'll explain to you. Yeah. So, okay. So every server has got a limited memory. Okay. They can only serve those many users which can fit in the queue and in the memory. Okay. So after a point of time, when the queue grows bigger, you may not be able to serve users beyond a certain time. Okay, so the availability is not something like yes or no. Okay, availability is more like what kind of how many requests are you able to reply to in 1 second. Okay, availability means that how many requests can you respond to the user. Okay, that is kind of availability, definition of availability. Okay, and the best 100% available system is where every request get answered in reasonable amount of time. Okay, and when you have because of the physical hardware restriction, a machine can only respond to a fixed number of requests. Therefore, a single machine is generally not highly available. Okay, we'll also talk about availability in other terms. Yes, you can say that in case of NoSQLs, the queue is smaller and therefore a usual database can cater to it. Okay, all right, very good questions. Do it make sense? All right, good, good, brilliant. Now, before moving forward, let's understand what does it mean by column-oriented database. Okay, so in a Excel sheet, right? In a Excel sheet or spreadsheet, how do we store data? Or when we export data into CSV, how do we store data? How do we store data in case of CSV? Yeshwant says row wise. Okay. Anybody else? Yes. Right. So row 1 comes before row 2, row 2 comes before row 3, and so on. I'm talking about strictly about saving the data in the disk. Okay, and the way it's saved is first goes first line, second goes second line, and so on. Okay, so in case of CSV, Excel, RDBMS, we have always been storing the data in a fashion where first row comes first, second row comes second, and so on. So all the columns of a row stay together, right? All the columns of a row stay together. If you have to find out the records pertaining to values of a row, it's quite easy. You just go to that row, get that value. But let's say I give you a CSV and I tell you, give me only the values of fourth column. Okay, and this data is quite huge. So you don't have any other option than going through the sheet from top to bottom, right? When I ask you, just give me just the fourth column, give me the values of fourth column, then you have to scan through the whole table. Such kind of databases or such kind of uh, format is a row oriented format, okay, where all the values of a row stay together and first row comes before the second row in the actual physical store and so on. Okay, now some of the data scientists realize that if we compress the values of column together, the results are far better. There are two ways. One, we take the values of each row and compress them. Okay, we zip all records of each row and keep them. While the other approach is you copy paste. Let's see the experiment. So you copy paste each row, zip it, and keep it. Okay. Similarly, you do another work where you take the columns and then compress them together and keep them. Now, what did scientists observe is when they compress the data column wise, it's far more powerful, is far more efficient because they found out that in a column generally all the values are similar in nature, and the way compression works is by eliminating by removing the similar values and replacing them by a symbol, right? That's how compression works. The way you must have seen that in a song, if a line is being repeated, instead of repeating the line in the lyrics, you just mark it -2, right? So similarly, the way people compress the lyrics by putting -2, repeat 3 times, and so on. And you sometimes see the in lyrics you put x7, which means this word has been repeated 7 times. Okay, so in the same way, the way people you see the lyrics being written sometimes, in the same way the compression happens. All the things which are common and repeating many times, they're replaced by a single symbol. And if there are multiple things occurring together all the time, you represent all of these multiple things with a single symbol. So that's the definition of that's how compression happens. Now, when you have a column which has all the same similar kind of values, right? You could represent that with a single symbol. Okay? Imagine that all the people are having only two genders. Okay, male and female. Now instead of, when you compress this data of the whole column, male female, male female, and so on, it's taking too much of space. Okay, so if you compress it together, what will database do? What will database do is it'll replace male with 0 and female with 1 internally, and then use 0 1 instead. So suddenly your database size grows to a very small size. is suddenly is reduced to very, very small. Now that is the important part of storing things in column wise fashion. And so because of the compression and because of the usage pattern, people found out that when you store things, when you compress things column wise, it is far more efficient. So they started storing data in column wise fashion physically. And these kind of databases are generally called column oriented databases. Perfect. So you can see here, so that was a little theory. So you can see here that employee ID and name. So employee ID 10 means Joe, and 12 Mary, 11 Kathy. That's being represented as 001 10, Joe 002. So you can see row number 0. This is every row is marked with a number. So row number 0 comes first, then row number 2, then row number 3, row number so on. Okay, I'll try to put it bold so that we can differentiate. Okay, you can see that this is the row oriented way of storing data. Okay, because at the end of it, the way we are going to store it is in bytes. Then comes the column oriented way of doing things. Column oriented meaning, here you can see first is this column. Okay, right, and then is the second column. So first you stored 10, 12, 11, and then you stored Joe, Mary, Kathy. All right, you can see that. So this is column oriented way of storing data. Biswa's question is, does that mean we need to have a lookup for hash code we generated for column values? We need to look up for hash code. We're not generating hash code for the column values. So internally, I was talking about the internal compression. You do not have to worry about the hash code because when the compression happens, database takes care of the compression. Okay. So probably you are thinking that we are the the way compression is happening. Okay. So now I think I now got it for your question. So probably the way you're explaining that it would be a similar way. Maybe the compression is happening internally, figuring out that are these two values same or not based on their hash code, and then doing the compression. But in compression, the techniques are a little different because hash code is costly affair. All right. Okay. Good that you got the answer. I'm happy. All right. Next is okay. So this is one example. Now let's move on. Now, there is another kind of database called column family oriented database. Okay, column family oriented database. Okay, so column family oriented database are something very interesting. HBase, which we are going to discuss now, is is a column family oriented database. Okay, so when some database said that, hey, it should not be my concern how user wants to store database. Let me give them a flexibility of both the worlds, column oriented as well as row oriented. Okay, so what HBase did was something very political and something that is really appreciated. They said that, okay, let's have something called column family. Okay, it's column family oriented database. All the data in each column family stays together. If If column family has only one column, each column family has only one column, that means that means that the it is column oriented. If all columns are in a single column family, then it's row oriented. Let's take a look at what does it mean by column family. Look at here. Here you have CF1 and CF2. Do you see CF1 and CF2? These are two column families. First column family is employee ID and name, and second column family is age. Okay, so first column family has two columns and second column family has only one column. Now CF1, all the data in CF1 gets stored together. What does it mean? It means employee ID and name are going to be stored together. What does it mean again? It means the data inside CF1 will be stored in a row wise fashion. Okay, so you will have 10 Joe, 12 Mary, 11 Kathy. Okay, the data inside CF1 will get stored first and then will come CF2. So the data of CF1 got stored in the form of 10 Joe, 12 Mary, 11 Kathy. Okay, then will come the CF2, then 22, 33 and 45 will get stored. Okay, so CF1 gets stored first, and in case CF1 has columns more than one, then those data will be stored in a row wise fashion. Okay, all right, so all right, so if we have, I'll try to make another sheet. Okay, all right. So if we have, how do we merge it? Okay, all right, all right. So you can see that, you can see here, what do I mean? So you can see that the data here will be stored in a column wise fashion or row wise fashion. Anybody? This one is? Yes. So yes, this is column wise, and this one Anyone? This one is? All right. Okay. So that is the clever thing. That's the clever thing column family does, right? That's a clever thing, and that's what HBase has adopted. All right. So a quick overview of HBase. HBase is as per the CAP theorem, HBase is CP, meaning it's consistent and partitioned, but not highly available. Highly available in the sense that you will see that although the definition of availability keeps on varying, okay, so it's consistent and partition tolerant, but not highly available. We will see that why is it so, okay. It's a column family oriented database, meaning it can behave in both fashion as column oriented and row oriented. Okay. It is based on Google's big table. It's good for hundreds of millions or billions of rows. Okay. It's good for that kind of data. It's strongly consistent. Reads and writes are not eventual. It's not eventually consistent. It's consistent reads and writes. Okay. Unlike MongoDB where the consistency is eventual, here it's not. It's strong. Okay. It's there is automatic sharding, as in the data gets splitted in automatically, and it has a great integration with Hadoop. it, it provides you a computing using MapReduce. It has a way of executing MapReduce by itself, and there are APIs, simple API in which you will get and put the data. So to disappoint you upfront, let me tell you that it does not provide SQL. There are third-party SQL with which you can query data from HBase. You can query data from HBase right now using get and put, which is very rudimentary. It sounds like a big step backwards, but with respect to load, HBase is pretty good. Okay. Next is coprocessors, and it provides you coprocessor similar to what we have stored procedures, and then it provides you further enhancements to search using Bloom filters. All right. Yeshwant's question is, yes. Yashwant's question is, since data is split into so many tables, won't this result in many joins? Yes, that's a good point. But as you will notice as we go forward, the architecture with respect to HBase is a little different. It's a little different, and you will be surprised that they all try to avoid joins exactly for the same reason. All right, they all, be it MongoDB and be it anybody, they try to avoid joins like anything. Okay. Even the MongoDB's main query does not allow joining. Similarly, in case of HBase, they don't provide out of the box any solution for HBase other than MapReduce. Okay. All right. So let's get into the architecture after the break. All right. So let me just write it down. Break for 10 minutes. Back by 8:43. All right, so should we start now? Yeah, is everyone back? Should we start now? All right, great. Yes, okay. All right. All right. So yes, Bishwa, your answers were correct. Okay. Yes, Midley, if a column family has two or more columns, it will be row wise. Yes. All right. Great, great. Okay, so all right. So the other thing which I want to discuss was the H-based architecture. All right. Now, when we talk about H-based architecture, the first important thing to know that HBase stores data in HDFS. Okay, it stores data as if you and me create the folders and stores it. Okay, I'll show you that. So, under the hood, the way normal databases store the data in the files. Okay, you talk to the database in the form of rows and tables, and the database, the same MySQL, stores it in a file with the same name as the table name, and so on. Similarly, HBase stores data in HDFS. That is the first thing. So, HBase, this boundary you see, it depends upon HDFS. Other than that, it depends on a service called Zookeeper. So Zookeeper is something like for coordination. Okay, we will talk about Zookeeper a little while later. Okay, okay. So here, the if you look at this diagram, it has got master and region server. Okay, so there is something called edge-based master, and there are many region servers. Okay, thank you, Yashwant, for letting us know. Now, are you able to see? All right, all right. Sorry for that. I had actually still paused the screen or showing you the pause the screen. All right. So here you can see that you have master and region servers. There are many region servers and there is single master. The data inside region servers is stored in the form of something called H file, mem store, and write ahead log. That's the internal data structure that they are using. More important than that is that there the it provides you a great API, and this API is accessible from various ways. Either you can talk to directly using Java, or you can use console to talk to HBase. Okay. Now here in next thing is that how does this conversation happen? So there are many region servers and one master. And whenever a user is asking anything, they always go to the master. And master gives access to those individual rows in each region. And then the user goes to region server and reads the data, and region server effectively reads data from HDFS. All right. In the similar fashion, when you are trying to store any data in HDFS, it stores data in very many regions. It splits data into many regions. And how, in what form do you store data in this in HBase master? We store data in the form of rows, many rows, as in, although there's a row ID and then the row. So we'll talk about data organization again. So master divides the data, and that data is stored inside region servers. Okay, so you can think of a big table being sliced into small chunks and being stored in region servers. Now what's the role of this zookeeper? So instead of these guys, region server and master, directly talking to each other, they talk via zookeeper. Okay, so zookeeper is kind of a whiteboard on which every region server writes its name. Okay, so are as in when region servers are up, they write their name on zookeeper, and master will see, oh, these are the zookeepers available. Sorry, these are the region servers available right now. So master will see this whiteboard called zookeeper. In on this, master will see, oh, these are the zookeepers available to me. These are the region servers available to me, and will use them instead of everybody reporting to master. Every region server informing master that, hey, I'm available. Instead of that, all of these nodes inform the zookeeper, and that's how it works. Similar to this, so zookeeper is kind of a general, you can say, coordination system or attendance kind of a system, where everybody informs about themselves to the zookeeper, and whosoever wants to query, they query from zookeeper. For example, to discover the data node, to discover how many data nodes are available, name node has started using zookeeper. Okay, or by default it does not use, but you can configure it to use zookeeper. So this system whereby coordination is required, that is handled by zookeeper. We will go into the details of zookeeper again. Right now you can see that the coordination between region servers and master happens through zookeeper instead of direct binding. Okay, so this is the very simple architecture of HBase. Yes. So architecture of HBase is very analogous to the HDFS. In HDFS also, you designate a master and many slaves, name node and data nodes. Here also you designate, this is my master and these are the region servers. And region servers are little dynamic, similar to data nodes and so on. Okay. So initially, all right. No, tables does not mean column families, Yashwant. Table have many column families. Okay, so the way this table has three column families and that one has one column family, unlike Cassandra. Okay, all right. So let me try to define what does it mean by regions and uh, region servers and all that. So So tables are automatically partitioned into regions. Okay. Tables are automatically divided into regions. And each region comprises a subset of tables rows. Okay. So this region is the unit of, transportation. This this is like a slice of the table which will be moving around. A region is denoted by table it belongs to, it's first row inclusive and last row exclusive. When I say my reason server is from 1 comma 3, it means third row is not included. All right. Initially, a table comprises of single reason, as in initially when we have a table, this is something very different. So initially we have a table which comprises of one reason only. Okay, there is only one reason because it has only hardly few records, and as and when we keep adding data to this table, and the moment this table grows beyond the size, minimum size which we have defined, it's not number of rows, it's the size of the row. Okay, if the reason, so initially one table and only one reason, no slices, no slice, initially a single chunk. As and when we are adding more and more rows, or we are updating existing rows, putting more and more data, the table is sliced into two. Table is sliced into two just from the middle of it. Okay, just from the middle of it, the table is split, and and new reasons are created. Okay, new reasons are created. All right. So again, keep in mind that in database there are always in there are always row IDs. Okay. So let me try to see if I can explain to you this mechanism. All right. So initially, let me just grab a. All right. So all right. So initially there is only single table. You can see that, and after some time you have added more and more rows, more and more rows. Okay, after that it will be sliced into two parts. It'll be sliced into two parts. One, this one, and it became two reasons. Okay, or let me just, I think this will be better thing. So let's say there is a table which has these many rows. Okay, so the moment it reaches say certain threshold, the size of it is increased. Okay, or let me try to say 1, 10, 12, 34, 45, 9, 80, and 100 and 123, and say 1 1, not this, and then we have 200, 234. Okay, as the table is increasing, now there will be two parts to it. Imagine that the editor which I'm trying to create here is two parts to it. All right, now you can see there are two parts to it. One this one and other this one. So let's say these many records are moved to. Now there are two reasons. Okay, this reason is from let me just denote this reason. It is from 1 to 46. Okay, it is from 1 to 46, and this reason is from 80 to from 80 to 235. Okay, 235. I'm putting a round bracket to denote that the last value is not increased, not there. Now, when the data gets, this is reason number one and reason number two. These are the two reasons right now. Okay. Now, master keeps on receiving more and more requests. Master keeps on tracking that reason one represent 1 to 46 and reason two is representing 80 to 235. There could be more columns here, more columns here. Okay. Right now, we are only talking about row ID. Okay, the as every record has one identifier, we are right now talking about this. Okay, this could be lexical, as in it could be textual. Right now we have just taken numbers for simplicity. All right. So initially there was, let's say there was 235 here, and all the records in one. And as and when the data was growing, it reached certain threshold which we can configure for our HBase. Okay, so data is split by itself. And second, and there became two regions. One, from this range to this range, and from 1 to 46, and other from 80 to 235. All right, now let's say more records come in. Now HBase master knows which record go where. Okay, yes, I'll show you the HBase table after this. Okay, all right. Now we could add more and more. Let's say 1,000 comes into play. Okay, let's say somebody adds 50. So 50 goes. Okay, 50 goes, let's say here, or let's say here. Okay, and the let's say somebody adds 33. 33 is added here, and again somebody adds 11, and then 13, then 14, 15, 16, and again we reached some number of records. Again this table will be split into two. Okay, this table is going to be splitted into two. Okay, now let's see how it looks. Okay, so now we got one more table which is starting from 15 and up to say 46. Okay, just for the reasoning sake. All right, so I think here it'll be for 50. Okay, never mind. All right, so here you can see that the first one has split it. Now, as the data, the important part is as the data is growing, both these sections will start splitting by itself. It will become, say, 15 here, and the rest of things are here. And it'll be, sorry, it'll be 50 actually, because the last record which has gone into another one is here. Okay. So we clearly know that if somebody is asking for adding 49, we add it here. Okay. So this way, HBase will keep track of the data what is where. So right now we started with one reason. So this is a single reason, single server, single table, which has got how many records? 7 plus 6 plus 7, which is 20 records, right? These are 20 record spread in three regions. If had it been in case of our usual database, it would look like this. It will look like this. Okay. Had it been our own kind of, you can see that look like this. All right. Will be 18 record in a single table. There's a single column right now. Okay. There's a single column right now. Make sense to you? No? All right. Any questions at this point? Biswa, I didn't get your question. Now we have to update. We have to update the definition of the reason, saying that when the reason splits up, you have to update the definition of the reason. All right. It should be, yeah. Question from Mamta is, the range says 50, 50, but data 50 is in table with the range. Yes, I'll tell you. So that here we said, you see the round bracket here, it means this record, the right limit, there are two limits like left and right, and if you remember the left right calculus, so here number line, here we are saying 15 is included but 50 is not. Okay, similarly we are saying here this needs to be updated, that's correct. We are saying 50 is included but 235 is not. Yes. A question from Biswa is, when will it split the data? We define that, and I think by default, it's around 256 MB. Okay, you can see it in the Ambari, those config details. Who controls the management of regions, developer or the base? So by default, HBase, but developer can intervene. Okay, developer can intervene. All right. So tables are automatically partitioned. Tables are automatically partitioned horizontally into regions. Each region comprises a subset of tables rows, and a region is denoted by the table it belongs to, its first row which is inclusive, and the last row which is not inclusive. Okay. Next is, initially the table starts with one region. As the size of the region keeps on growing beyond a certain threshold, the table is equally split into two halves. Until the first is split, loading is against a single machine. Okay? And as the table grows, the loading becomes against many regions. As we are adding records, the records will be added parallelly onto every region. So if there are a lot of traffic, the work is delegated to region servers. But HBase master controls HBase master controls which which region has which IDs. Okay, so as the data grows, number of regions grow while table remains same. All right. Now question from Biswa is, table is partitioned horizontally or vertically? Table is partitioned horizontally. All the data is stored on one node. Is it in HDFS? No. The data is stored in HDFS file, which internally is having multiple copies. All right. All right. So here, this is the another way of looking at the region server and the view. You can see that. Yeah. So I meant to say that as the data grows, the the number of regions would grow. All right. And with respect to storage, whatever so at the end of it, every region is stored into the disk as a file, and every file is anyway replicated by 3. Okay, we will see that again. All right. So you can see that the reason server here, okay, they have divided and sliced the data into 6 regions, and there are multiple regions on a single region servers. Okay, you can see that there are two regions on every server. All right, so the most important part to understand about HBase is the data model. As per the big table paper by Sanjay Gemawat and Jeff Dean, so the paper clearly says probably the best definition of big table. And since HBase is based on big table, the definition is still valid. And the definition is probably the most crisp. I can't remove any more word from it, and I don't need to anymore add any more word to it. Okay, so the definition is probably most crisp. So it says that it's a sparse. What does it mean by? So let me explain what am I trying to explain. So we are right now talking about the data model of HBase. Okay, what kind of data and what kind of structure it is? It's kind of the structure of data that we are going to talk about. Okay, so I'm taking the definition given by big table authors, which was a Google project where Google is storing all the crawled corpus, as in crawled data from all the website, because Google stores the data from all across the globe into their big table. Okay, HBase is modeled after big table. Okay, HBase is modeled after big table. So big table is sparse, distributed, persistent, multidimensional, and sorted map. Okay, so most important thing you need to understand about big table is it's mostly like a map. It's mostly like a hash map. What is a map? Collection of key value pairs. So collection is of key value pair where you can quickly look up for a key. Okay, so big table is nothing but a big key value pair collection, right? Big key value pair collection. Okay, which is sparse, which is multidimensional. Okay, let's okay. So I'll just go from right to left with all these properties, and that will make most sense out of all of this. Okay, so from right hand side, the definition is it's a big hash map kind of thing where you store all of the data. Okay, it has key and the values, and keys are sorted. It's a sorted map. That's the second keyword. It's a sorted map, meaning the data is sorted. As you saw in this, where is that? I think we removed that. As you saw here, the keys were sorted. You see that? 50, 80, 100, 123, and so on. Okay, so it's a sorted map. In our example, value was null and we were having only the keys. Okay, next is it's multidimensional. The values could be multi-values. Similarly, keys could be a composite key. Okay, so you could store anything in the values. You could create multiple columns out of values. Okay, and so on. The value could be a single value or multiple values. So that is what it means by multidimensional. Okay, so there could be many columns or there could be one column, and so on. Next is it's persistent. Okay, it's persistent, meaning it's not only in memory but it is saved on the disk. Okay, so in case you shut down the big table and start again, whatever records you saved earlier will be available. Next is it's distributed. This hash table or this data structure we have talked so far is distributed into region servers, right? Is sparse. What does it mean by sparse? The columns defined in one row, one for one row key or one key. So every row has one key called row key. We'll talk about it again. So the values or columns for this row, or in this okay, let's take the analogy with the map itself. Map has got key and the value. Key is also called row key, and value is the whole row. Okay, this value has multiple columns. This value has multiple columns, say column 1, column 2, column 3. These columns could be different. First row having name and uh, age, while second row is having name and uh, address, okay, and so on. So the values have dimensions, as in values have columns. uh, in this map there is key, there is value could be many columns, and these columns could be different for different keys, different for different rows. All right, so that's what is the data structure about. All right, so HBase organizes table into data into tables. Table names are strings that are safe for file path, because it's going to create a folder for table in the HDFS. Okay, a row within a table, the data is stored according to its row. Rows are identified uniquely by their row key, and row keys do not have a data type and are treated as a byte array. Okay, then the column family. Data within a row is grouped by the column family. Okay, data within a row is grouped by the column family. It impacts the physical arrangement of data. Okay, you have to define the column family upfront. Okay, you have to define column family upfront. Okay, and that is kind of the only schema you have to define while creating a HBase table. Okay, every row has the same column family. You cannot add more column family, or okay, you don't necessarily need to store the data in each column family inside a row. Okay, strings, okay, column family name has to be simple strings which are okay to be the file name, because again, for each column family it's going to create a file. All right, next is column name. Data within a column family is addressed by column identifier. Okay, and the important part which you should understand is the column name itself can store binary data. Okay, and columns can be inconsistent between the rows. All rows are not supposed to have the same, are not necessarily need to be having the same set of columns. It could be sparse. All right. Then the cell. Okay. So effectively, if you look at it, okay. So row are identifiable by the row key. This we have already covered. All right. So row key can have any data in that can have binary data. All right, so basically the data within a column family is addressed by a column qualifier. Column qualifier need not to be specified in advance. Column qualifier need not be consistent between the rows. Like row keys, column qualifier also do not have data type. They're always treated as byte array. Okay. Now the cell. The smallest unit of storage is cell. A cell is identified by which table is it, which table, which row, which row key, and which column family, which column name, and which version number. Now, and cell can have binary data. Okay. Now the version. Every cell can have multiple versions. Okay. Every cell can have multiple versions. Okay. Which by default is the timestamp. Yes, we'll have an example. Okay, which by default is the timestamp. And if it's not specified, the current time is used. So when we are storing the value in a cell, the previous value is moved to the previous version and a new version is created. And the version identifier by default is time. Okay, so you can think of every cell has got the history of 3. All right, and so on. All right, this is how it's going to look. You imagine that there is this table where is the row IDs are there. There is the name of the people, the phone number, residence phone number, and their office phone number and office address. It has got two column families. One is personal column family, other is office column family. You can see that personal and office. Okay, the row key is something which is identifying each row uniquely so that we can easily uh, decide what is where. All right, you can see that. So each cell has multiple versions, typically represented by timestamp of when they were inserted in a table and so on. So the way we are displaying right now, it looks like a row-based storage. It's the internal way it will be the way it would be stored would be column family oriented way. Okay. Mahesh's question is: are the region servers physical servers like data nodes? Yes, they are. I missed that question somehow. All right. So is it clear to everyone what is column? These are the columns. This is the column family. This is the rows, and these are the cells. Okay. All right. Again, you can see that the most important aspect of this is row ID. Under row ID comes the what do you call the column family, then the column and the timestamp, and for different timestamp the different values. So earlier, let's say somebody typed market in the value, and then later on they modified to this. Okay, so it'll keep a track of last 3 values by default, but you can increase that. All right. Now the most important part. Let's take an example. So Yeshwant's question is: can we see a real HBase table? It'll be better for understanding. It uh, yes. Is it allow update? Yes, it does allow update, of course. All right. All right. Let's take a case of the real case. Okay. I'll show you Yashwant in a minute. So this table structure is clear to you, right? And we also talked about the storage. We also talked about we can keep on. So the important part about few things we need to I'll be very informal about it. So in an HBase table, every row can have different set of columns. Okay, every row can have different set of column, and and it won't mind it. There's no reason, meaning two rows having two set of columns. completely different set of columns. That's completely okay. Second thing which we should understand about HBase, that this is the because rest of the things probably all of us are aware, right? We all are aware about the rest of the systems. The other thing which we need to know is that you can keep on adding columns as well as rows. You can keep on adding as many rows as you want, and you can keep on adding columns, meaning for each row can bring more and more columns. So it's like a matrix. It's like a matrix where you can keep on adding rows and columns without having to worry about overflows. Okay, so that's something important. That instead of thinking about that when we are adding row when we are adding a column, we have to update old rows. No, we don't have to. Okay, so you can think of always like a big key value collections. All right, let's take a real example. Every row means row within a column family. Sorry, row within a table, not column family. Every row is row within a. So that's a question from Yashwant. Question is, every row means row within a column family or row within a table? Answer is table. Okay. All right. Let's take a real example, something for which the whole invention has happened. Okay. So look at this table. What exactly is this? This table is what the reason for at big table invention. This table contains the data from all websites, okay, crawled by Google. Google downloads websites data from all websites across the globe. Then it figures out who is referring to which website. If a website is referring to some other, the other website gets bigger rank than this one. If my website links to your website gets vote from me. Okay, I increase your website's value. If that's why I always request all my students when they're creating a GitHub project to link no big data in their readme. Okay, that increases the value of no big data, because that increases the value of no big data in a tiny little fashion. All right, so coming back to it, so this is the table which keeps track of who is referring to who. So Google downloads these web pages and keeps on preparing this relationship. And how does it do it? It has two column families. One called contents, other is called anchor. Okay? And the row is the URL. All right. So let me take a step back. Let me try to explain. Okay, imagine you have three websites. Let's say nobigdata.com. Okay, and then we have microsoft.com and bing.com. Okay, and let's say Hortonworks and let's say yeah, Hortonworks. Good. So these are the three websites. Now, when Google went to no big data, it found a link to Hortonworks. Okay, so we have to remove one R. Okay, hortonworks.com with the name, say, VM. Okay, okay, download a VM from there. Okay, so that's the name. Then it went to Microsoft. There will be a lot more things I'm keeping for simplicity. Okay, there will be a lot more HTML. Now it went to Microsoft and it says href equals to. Okay, so Microsoft.com if you go to Microsoft.com, you'll find a link to Bing.com. Okay, and we'll have title of that link will be search engine and so on. There'll be a lot more links to this. Now it went to Bing.com. There it found that okay, that there is no other link. Okay, let's say there is, it's pointing to nobody. Okay, now next is Hortonworks. Hortonworks contains a link to Microsoft.com with the name called HD Insights. Okay, now you can see that Hortonworks is referring to Microsoft. Okay, and we are referring to Hortonworks. So effectively, Microsoft gets the highest value out of all. Okay, is that clear? Now let's say there was this page collection which we have to, let me just put it in my notes. Okay, let's say we had this huge page collection of millions of pages. Now we want to store all of this information somewhere so that we can use it. Okay, in case of in case of here in case of HBase or big table, what we would do is we will create a table. Okay, we'll create a table. Should I create an Excel sheet? Will that be a good idea? Or should I create in Microsoft Excel itself? Because that will be more similar to what we are trying to. Okay, let me try to create it in Excel. All right. Okay, let me increase the font a little bit. All right, you can see that. Now let's go back here. Okay, so no big data is referring to Hortonworks. Okay, so we'll go to Hortonworks, and you can always think of this as contents. Okay, contents is our the contents is our column family. Okay, contents is our column family, and yeah, and then we have what do you call the other column family is anchor. Okay, so we can see that here in this case, this is the row key. Here, Hortonworks Hortonworks is being referred by, so Hortonworks will be referred by who? No big data. Where is no big data? Here is no big data. No big data is the column name. Please note that this is the most important aspect this I wanted to demonstrate. So these are the columns, okay, and these are the column families. You can think of this way, and can we merge it? How do we merge? Okay, yeah, okay. So whatever content it encounters in Hortonworks, it puts it here. Okay, this is the HTML content it encountered there, and then it puts back who is referring to who. Okay, so it shows that no big data is referring to Hortonworks by what name? By what name? By the name of VM. Okay, so similarly, while Microsoft is being referred by Hortonworks. How is Hortonwork referring to Microsoft? As HD Insights. Okay, so you can think of this way. So this hotandworks.com, where were that hotandworks.com? All right. So please pay, yeah. So hotandworks is the column name. Similarly, no big data was the column name, and and the cell value was the name with which it was it was referring. Okay, you can see that. And then HD Insights, to Hottenworks is referring to Microsoft.com with the name called HD Insights. All right. Next is Microsoft.com or Bing.com. Let's go with Bing.com. Bing.com is being referred by Microsoft.com. So Microsoft.com becomes a. I'm just removing this for some reason. Okay, for making it clear. Okay, so Bing.com is being referred by Microsoft.com. Okay, with the name as search engine. All right, good. All right, so we are basically creating a two-dimensional matrix where on x-axis you have the referrer, on y-axis who is referring to who. Okay, that's what is happening. So no big data is referring to Hortonworks with the name as VM. Hortonworks is referring to Microsoft with the name as HD Insights. Microsoft is referring to Bing.com with the name as search engine. Okay, now we have a clear structure saying who refers to who. Okay, now question from Yashwant is that what will HTML and PDF contain? Okay, so just for the example sake, because we want to store many properties of the page, Google wants to store many properties of this page. Okay, such as what was the actual content that was downloaded from Hottenbox, the whole HTML would go here. HTML head, title, and so on. Okay, all right. The other important part which we missed was that these will be in the order. So first it will be Bing, then it will be Microsoft in the alphabetic order. Sorry, this will be at the top. Okay, you can see that. So here you can see that first it would be Bing, then Hortonworks, then Microsoft. Okay, and here it'll be like if while downloading data from Bing.com, whatever PDF it encounters, it will put here. Or you can say content, as in you can say HTML web, or it could be HTML mobile. Okay, what are the different kind of HTML this website is giving us when we are visiting from the mobile or the web? Okay, so this way we were able to store relationships between two sets of data easily using a single table. Is that clear? No? Similarly, so this is basically we have drawn kind of a sparse matrix. That's right, Yashwant, that we have drawn it. Okay, this is something which took me some time to understand. when I first encountered HBase or Cassandra for that matter, so when I started working Cassandra, it took me some time to understand that, oh, we can create as many columns as we want. That was the first enlightenment. Second enlightenment was every row can have different set of columns. That was second. Third one was interesting. Third one was we can store any data inside column. Okay, while we are creating here only with the strings, every time we are creating a name, column name with the data. Okay, you can see that. Okay, so instead of that, we were actually storing binary data in the column name and row key. Row key, even though it looks like a plain text, row key can be binary. And the way the ordering would work on that binary is using state 0001 kind of a method, because every bit can be ordered. Similarly, bytes can be ordered in the same manner. Make sense to you? Good. So it's clear to Biswa, it's clear to Mamta, and it's clear to Yashwant. What about others? Yashwant, is that clear? All right. Mahesh, Midley, and Prezi, is it clear to you? All right. Yes. So we keep adding columns to column family. That's right, Yashwant. Yes. Okay. So Biswa's question is, can we take a look at the actual data stored in file for this example? Okay. Do you mean you want to see this one? For this example, this is the one. Okay. You mean to say in HDFS? I'll show you a couple of examples in HDFS. All right. All right. I'll show you on the HDFS. All right. I think what I should do better is, yeah, one more tiny little bit which I missed and I have been waiting to explain. Now, in this example, what you noticed was that if somebody has to, okay, so one more thing I wanted to say. Let's say there is another domain called mail.bing.com, okay, and say web.bing.com, okay, mobile.bing.com, right? All these will become very, very, very distant, right? They'll become very distant. Okay. All right. Now you can see. So you can see that if you have to find out, imagine that there are 1 million such websites. Okay. So all the subdomains of Bing will get lost, right? Mail.bing.com, web.bing.com, mobile.bing.com, and so on, they have become separated. So if you just have to find out all the URL or all the content of bing.com, then it'll be very, very difficult, right? Therefore, here you have to play a little bit clever by tweaking what is your row ID. You should create your row ID in a manner that the data belonging to something comes together, right? The way we did a clever thing while creating MapReduce, in the same way, you have to figure out a way to keep your data close to each other, because the data close to each other is going to go in regions, right? If you remember, each region will be from one ID to another ID. So the data belonging to the same website, chances are, if if the row ID is same, if row ID is in the sequence, then it should be together. Otherwise, data will be completely sparse and you won't be able to find data for bing.com. That's why Google guys did a clever thing here. And similarly, whenever we encounter a problem, we figure out how should our row key be so that the data which you want to keep together should be together. Okay, although we will keep the data together, the values together by the way of defining our column family, but rows should also be kept in the same manner, because data belonging to consecutive rows can be fetched together. Okay, therefore you should be a little careful. And hence what did Google guys did? They inversed it. They did an inverse thing. Okay, meaning this became com.bing.com. Okay, let me just remove .com from everything, and okay, and then we'll say and anything followed by dot, then anything. I'm just writing a regex to automatically swap it so that I don't have to swap it by myself. Okay, see that? So what they did was they stored the data in this fashion. Com.bing, instead of saying bing.com, com.bing, com.bing.mail, and so on. Now you can see that. Okay, so when it gets sorted, then this data will come here. All right. All right. So yeah, com.bing.web. You can see that com.bing.mobile. Okay, and here it'll be com.hotandworks. Now you can see that the com.bing, all of this data has come together. All right, because the data is sorted by the. Okay. So that's another advantages. Correct? Yeah, this will be little after this. Okay. How do you generally do this? I think it'll be here. Okay. All right. I think this is correct now. Com.bing, com.bing.mail, com.bing.mobile, web, com.hotandworks, com.microsoft. Perfect. All right. So what we just saw was that we tweaked our row ID such that the data belonging together stays together. That's what we did just now. Okay, that's what we did just now. All right. Any questions at this point? All right. So that was our example, and we our attempt to do this. So here basically row key is a reversed URL. Contents column family contains the page content. Column name is blank, which is acceptable. Okay. Anchor column family contains the text of any anchor that references the page. CNN CNN's homepage is referenced by both CNNSI and mylook.ca. One more thing we missed earlier, that two pages could also link to one page. That means there'll be two columns. Okay. Each anchor cell has one version. Okay. Each anchor cell has one version. The contents column has three versions at timestamp T3, T5, and T6. Okay. If one more website, xyz.co, refers to cnn.com as news, then it will have one more column called this. Okay. We've already discussed this part. All right. So, so also the other way of looking at the data was this. Okay. Yeah. So row key was this. We could have multiple timestamps for the same key, same column, and we could have different values. Okay. So column family contents look like this. Okay. So these are various timestamp, various values. That's what we are trying to demonstrate. Now let's try to show you a little bit about how does a table look like. All right. Let me just log into my account. Okay, let me just look at my account. All right, so here we go. So this is the login, and for this login, let's open a console. And what is the Ambari hue, etc. All right, so we could say HBase shell. Yes, my question is because table is sparse, we are not concerned about data size as we are using HDFS. That's correct. We are not using HDFS. It says 5 servers are dead, 2 servers are alive. That is strange. Let me open Ambari. I'll have to go into admin. I'll freeze the screen for a second, and so that I can enter. All right, let me just see why it's not working. It says HBase is done, standby is working. 2 out of 2 region servers are up. That is strange. That's all right. That's okay, I think. Yeah, it's okay. Right now there are only 2 region servers. We should ideally install more region servers. Okay. All right. So here we are. Okay. Now let's say, so let's try to see the status. Now let's try to create a table. Say create a table. What does it say? It says the table already exists called my table. This table is already existing. Let me try to change things a little bit for only this session. Okay, so we'll say 12 December, okay, and 7. Okay, so let's just create a table with this name. All right, let's just create a table with this name and see what's happening. All right, so we could say list, and there is our table. You can see 12 December. Also, we could say things like list dot star, and we could say 7. Okay, okay, so there is only one table that's matching dot star, which is 12 December 7. Okay, so we could also say things like that. And now if we have this table called 12 December 7, I think we can say, okay, so we could say things like put into this table, into this row, and this data. Right now we have only defined one thing called a column family. Okay. Okay. Now what we have done, we have uh, added added 2 rows, row 2 and row 1. Row 2 contains only one column called column 1, and row 1 contains only one column value called column 2, and so on. So, and we are saying for this column family add this value. If you have 10 column family, you can put 10 times. Okay. Now we can scan this value easily. You can see that we're able to scan the table. If you want to get a particular value, you can easily get that value. Okay. There is no column value for column 1 in row 1. So we could say here column 2. Alright, you can see the value. MyCF, okay, what is MyCF? This is the column family. So while you created, so we started the HBase shell, we checked the status, then we said create a table called 12 December, which contains only single column family called MyCF. All right. And then we said put the data into this table, into this row key, into this column family, for this column this much. That's it. Okay. Similarly for this one. Okay. So we can always say scan and 12 December 7. See that? We are able to see what's there inside it. Okay. Also, you could say things like put in the same column, in this same column family for the same row. Okay, I'm saying column 3. Now you see scan 12 December. See that? Alright, Yashwant's point is, can you put another row for the same column? Okay, yes, we can put another row for the same column. Let's say column 3 and we can say row number 4. Yeah. Alright, let's try to do this. Now we can say scan. Alright, you can see row number 4 having this and this value. Make sense to you, Yashwant? Is it clear to everyone? So Biswa is saying, can we put another value for row 1 for column 1? Row 1 for column 1. Let's say, okay, let's put it. Alright, let's say we put something, some junk. Okay, you can see that. So row 1 has column value x1 and this. Good? Now, Yashwant's question is, how do you read these values in the program and make sense out of it? There are two ways. One is use the straight API, getPut API, provided by Java for this. Or what you do is you basically use the HDFS, okay? Use the third-party software to do that for you, okay? Now going back to the, all right. So now we can describe the table, whatever the table we had. We can say describe this. Okay. Let's go to the console. Describe this. It's showing you the clearly that there's a name of the column families. Okay. Every column family has got these descriptions, and the block size is this much, meaning in case the data grows beyond this, it's going to create more reasons. Okay, now we can disable our table. You have to disable a table before dropping so that all the connections finish gracefully. Okay, so we are able to delete it. All right, you can see the status at, what is that? I think c.nobigdata.com. Not no big data, it's cloudxlab. Cloudxlab.com. Either B or C. Oh, it doesn't allow. Okay, so let me just, we have actually blocked a lot of HBase port unblock. All right, so that was our quick. Okay, we have blocked all the ports. Yes, we can create one more column family, but for that you could actually use say hue. Okay, you could actually go into hue. You could use that one. So let's say I go to data browser, go to HBase. What is the name of a table? Where is the table? Oh, we have not. So it's somebody else's table. All right. So you can add more tables from here. You can, from the UI as well, you can start creating the tables. Okay. And I'll show you this. So you could create a new table, say my table, or let's say 12 December, and family name is say personal details, and then we say official details, and so on. Okay, these are the two column family we created, and then we could say 12 December. Under this there are two official details, and this under this we could, all right, there is a way. Okay, you can add. Okay, so I think you can official details filter. Yeah, here is the new row. Yes, we deleted the table. Yeah, earlier. So yeah, you could add row one. Okay, and then you could say CF1 column, some column name, and so on. So here you will have to say personal details name Sandeep, and then we could submit. So you can see that there is a column family called personal detail, there is a row called row one, and there's a detail. Okay, so same thing is available as a web interface to you. Okay, we could further say, even we say row one. Okay, and say office details. What were the name of the columns? Is it available somewhere? Office details, and then we say, all right, it, what does it say? Okay, maybe the row does not exist, or what? Office detail is does not exist in the region. Oh, that's a little scary. So first official detail is not. Yeah, row one, and we say official details, and we say that's it. You can see we are able to add the details in the same manner. All right, you could even bulk upload a CSV and import the data into this. All right, so there are many auxiliary programs. Yes. Question from Yashwant is, can we use, yes, thank you Biswa, thank you Mamta. All right, so question from Yashwant is, can we use this in Pig and Hive? Yes, there is HBase loader in both Pig and Hive. Okay, there's a UDF with which you can load it. All right, so we are almost through the HBase. Also, you can look at this location, we can look at this location and find out that the data is actually stored in HDFS. So we can go to say query file browser, all right, here we have 12 December. So under this, for our table called 12 December, it has created a folder. Therefore, you should always keep the table name as very clean. Then under that, there's something called the reason ID. Just after the table, there is a reason. There's a reason number generated for each ID. Under the reason, there is the column family. You see, official detail, personal detail, and then the summary covered edits. Okay. For each reason, there is sorry. These are column family details. So table, reason, column families. Okay. Under column families would be your data. Okay. So it'll take some time to reflect here because it's still in the TMP probably. Here is it is in TMP somewhere. Okay. So have I closed things? All right. Where is the Edge-based data browser? I think it'll take some time to flush the data. All right. It would have stored somewhere. Okay, so that's how the data is stored. So under the table there is a reason, under the reason there is a column family name, and then under that there are store files. This is where the actual data is stored for each column family. For each reason, for each column family, there is a for each reason, for each column family. Okay, there is so first you slice the table horizontally and then you slice it vertically into reasons and put it there. Okay, and for each column family, first you cut it horizontally by the reasons, and then you cut it vertically in the column families, and then they save the data in store files. Okay, so that's how the data is stored physically. Rows updates are atomic. No matter how many row columns constitutes a row level transaction, the the data will be per row, the commit will be safe. Okay, so you can create the scanners to scan the data. We'll go through these details and we'll continue our discussion from this slide onwards, 33 slide onwards. Okay, all right then, have a good day. Bye bye. Yes, Yashwant. So yeah, Yashwant has a question. All right, sure. We'll try if we can get this data via PIG or UTF. Okay. In the meantime, you can give it a try. There is a H-based loader and H-based catalog. In the first session, we talked about it. You could try doing that. All right. All right. Good. Great session. And thank you all. And feel free to, you know, give the feedback. All right. Bye bye. Have a good day. I think 3 more sessions are left, Biswa. All right.